let's take a look at and work some examples in your on that worksheet. So the first one, it says at a Haltom football game versus Richland, the cheerleading squad uses their t-shirt launcher to launch some t-shirts up into the stands. The football field, from the football field, they have an initial angle of 30 degrees. Assume gravity is 10 meters per second. What's the maximum height? How far away could the t-shirt land if it was landing at the same height? And how long could the t-shirt be in the air? So I'm not going to actually shoot it up into the stands because then we have differing heights and you guys can't work that problem quite yet. You will be able to though. But let's assume that we're launching it up and then it's landing at the same height. So how would we do that? So I like to do, on all projectile problems, I like to separate out the horizontal and the vertical components. The horizontal and vertical components are completely separate. There's only one thing that joins those two together, and that's time. So horizontal motion is at constant velocity because there's nothing affecting it. There's no gravity that affects how fast something moves back and forth. But vertical motion, we have gravity, right? We can shoot it up, we can shoot it sideways, or we can shoot it down, and we start with some velocity. Horizontally, the velocity is 0, but if we shoot it up, it has some positive velocity. Gravity eventually stops it, it has 0 velocity, and then it starts to have negative velocity as it comes back down. So I'm going to separate those two when I'm identifying my variables and when I'm solving for the questions that it's asking. So the first thing is, how do we get the velocity in the y direction? So the velocity in the y direction, if we're looking at just let's look at a diagram of what's going on here. So here we've got the ground, and here we have our initial velocity, which is v0, and it gives that to us up there. It says initial velocity of 65 meters per second. Now that's frightful, that's really high, okay? It's more like an arrow shot out of a bow than it is for a t-shirt launcher, but let's just pretend that that's a reasonable number. So V0 is 65 meters per second. Now some of that velocity is in the up direction, and some of that velocity is in the out x direction, right? So we need to separate those two from each other. We do that by considering that this is really a right triangle, and that on the bottom, down here, we have some Vx, and right here, we have some Vy. Since that's a triangle, we can use our sines and cosines. I know that Vy over V0, you don't have to write this down, I'm just going to show you what it is. Vy over V0 is equal to the sine of that angle, right? This angle theta. Because opposite over hypotenuse, right? You guys remember that SOHCAHTOA thing you learned? Okay, so opposite over hypotenuse is the sine of this angle. So if I rearrange this, multiply both sides by V0, then I end up with Vy is equal to V0 times the sine of the angle. Vx, on the other hand, that's the adjacent angle. So Vx over the hypotenuse, which is my V0, is equal to the cosine of theta. And if I multiply both sides by V0, my V0 comes over here and it cancels over here. And I end up with Vx is equal to V0 times the cosine of theta. Remember, V0 is the original velocity at that angle. And I'm never going to use that again. I've separated that into the x and the y velocity. And I'll never go back and look at that again. Because what I really need are the x and the y velocity. So my y velocity in the upwards direction is V0 times the sine of that angle, which the sine of 30 degrees, I commonly pick that because it's equal to 1/2. So it's easy to remember. is 32.5 meters per second. We know that gravity is equal to minus 10 meters per second squared, minus 9.8 if we're doing a lab, right? Because we want to use very close to the original. And then the question is, what is the time? And one of the questions, how far does it go? I'm going to have to erase over here to show this. It's a little bit cut off, but we know that if we throw something up in the air at the top of its arc, how fast is it going? How much? 0. Right, so I can use this to my advantage and calculate how long it takes to get to the top of its arc, because I know the final velocity is 0. I know the initial velocity in the y direction I've already calculated right here, 32.5 meters per second, and I know the acceleration. So I end up with 32.5 meters per second over minus 10 meters per second squared, and I get my time to the top of the arc. Remember, it also has to come back down too. It's 3.25 seconds. That's a long time in the air. But of course I told you that was frightfully fast for a t-shirt launcher. Okay, so with that, I can now calculate the height. And I'm going to substitute in my time into this equation. 1/2 final velocity plus initial velocity times t. This is really just the average velocity. That's what this equation right here is, average velocity. So I've just written it out. This is the same as distance equals velocity average times t. But what is my average velocity? Yeah, right there, right? If I take the beginning and the end and divide by 2, the beginning plus the end and divide by 2, I end up with the average. And again, look for equations on your equation sheet that you actually have the variables for, and that'll help you out. So I go on and I substitute in, and I end up with my distance in the y direction as being 52.8 meters. So we shot this thing 160 feet into the air. Okay, it's pretty high, especially since we were only at 30 degrees. So there's an answer to the maximum height. So I went on and put a box around it. Since I have the time, I can also get the distance over here. My Vy is going to be my 65 meters per second times the cosine of 30 degrees, which is 0.866. 0.866. So I end up with 56.3 meters per second. So that's its horizontal velocity. And that's what I'll use in my calculations from now on. Now my time that it's in the air is twice the time that it took to reach its highest point. So when something goes up and it takes some time to get up there, it takes the same amount of time for it to get down if it is coming down to the same level. Now if I shoot it off a cliff and it lands further down, that's different. But if I shoot something from the ground and it comes back to the ground, the two sides of that parabola shape, that arc right there, the two sides are mirror images of each other. They're mirror images of each other, including the angles and the velocities. So multiply my time times 2, and I know that it's going to be in the air for 6.5 seconds. So that's the answer to part B. Oh, actually, that's the answer to part C. How far away could the t-shirt land? That's an X question. Now that I have the velocity, the X, and I have the time, I can calculate dx with that equation. Distance is equal to velocity times time. If I'm going 35 miles an hour for 2 hours, 35 times 2 is 70, right? I went 70 miles. So, same thing with here, with the distance. If I am going 56.3 meters per second for 6.5 seconds, how far do I go? So I substitute in, and I get 366 meters. So basically, my t-shirt launcher launched the distance of 4 football fields. So not a real t-shirt launcher. Obviously, 400 meters is a long shot with a hunting rifle. It's probably a lot more like a small little bazooka than it is a t-shirt launcher. I'll have to change this next year. I like to give realistic numbers. This is not a realistic number. But anyway, so those are our answers. Notice I color-coded all of the horizontal stuff in green, including the horizontal calculations, and the vertical ones in blue. You don't have to do that. I did it to separate them. The best way to solve these problems is to separate the horizontal and the vertical. If you do not know time, you need to get it probably first from one side or the other. If you know the velocity and the distance over here, you can solve for time with this equation. But most of the time you don't know that. Alternatively, on this side, you can often solve for time if you know the height that it goes to. Okay? Or in this case, if you know the initial velocity, you can solve for how long it takes to get to 0. Gravity is sucking away at that initial velocity. When you shoot something up, gravity's pulling away from it, trying to get it to slow down. And when it reaches 0, we can use this equation right here to calculate how long it took. Pretty straightforward. Okay. I'm going to skip right to problem number 4. So let's go to problem 4. You should have this drawing over here on that worksheet. Projectile is fired from a height of 10 meters at a velocity of 10 meters per second and an angle of 30 degrees. What's its total flight time? So we're going to do all of this stuff on the vertical side. So first of all, we need to solve for the vertical velocity. So considering that this is a right triangle, the vertical velocity is the sine of the angle times the hypotenuse, which is V naught. And the sine is 0.5. Sine of 30 degrees is 0.5. So problem number 2 or 3, I think your angle is 66 degrees or something like that. So you can't use that half. But, you know, just plug in your calculator sine of 30, or sine of whatever your angle is, and you'll get whatever number goes there. Okay, so these are my unknowns. My time in the air is unknown. So I need to solve for that. Oh, and what's the height? I don't know how high it goes either. So let's take a look. The time in the air, we're going to use the same equation we just used. So my initial velocity turned out to be coincidentally or conveniently 5 meters per second. That's because of that sine of 30 degrees being 0.5. And divided by 10 meters per second squared for gravity. And I get the time to reach the top of the arc is half a second. Now, in this case, is the bottom of the arc a mirror image? Left and right, are they the same? No, they're not, because it's falling to a higher or to a further distance than where it was launched from. If it was landing right here, okay, if it was landing right here at, you know, what do we call that? I don't know, omega. I made that up. If it was landing at that point, then the left side and the right side would be identical or mirror images of each other. But it's not. It's going to pass that spot and keep going. Now, at this spot, what is the same? This angle is the same, and the velocity is the same, except in the opposite direction in y. Okay? It's still moving the same direction in x that way, but it's going down instead of up in y. So with this time, what we're going to need to do is we're going to need to consider how high did it go, and consider this like a horizontal projectile problem now. Because at the top of its arc, if I shoot something up in the air, it has some y velocity, doesn't it? Some positive y velocity going up. But when it gets all the way to the top and turns like this, now it has no y velocity at all, does it? Only velocity in that direction. And that's just like if I had a great big tall cliff right here and I did a horizontal projectile problem off that tall cliff. Okay? It's just like that. So now that I know how high it goes, I just treat it like a horizontal projectile problem. So I need to know that height. So the first thing I'm going to do, calculate the height just like I did in the previous question, or question number 1. I ended up with, it went up 1.25 meters. And now I need to know the total distance that it's going to fall from that height. So let's add that. We know that this cliff is 10 meters high, plus that 1.25 meters means it's 11.25 meters. So I'm going to use this in my new horizontal projectile problem. And I just need to do this. dy is equal to 1/2 gt squared. I rearrange that, and I get this. And you guys have seen this equation before, haven't you? Right? How to solve for the time. So how long does it take to fall from that height? I substitute in, and it takes 1.5 seconds. Very convenient. Now I'm going to take my 2 times, and I'm going to add those together. So it takes 1/2 second to go up, and it takes 1.5 seconds to go down. So I add those together, and I get 2 seconds for my total time in the air. Could I calculate how far away it hits? Well, sure, that would be really easy. If I wanted to do that, my distance, if I look at that original equation, velocity in the x direction is equal to distance in the x direction over time, rearrange it and say dx is equal to vx times t. So dx is equal to my 10 meters per second, that's my v naught, times my cosine of 30 degrees times 2 seconds. And that would be something like 8.66 meters per second times 2, which would make that something like 17.32 meters. I did that in my head. I'm hoping I got it right. If you guys have a calculator, you can check my work. But anyway, I know that the cosine of 30 degrees is like 0.866. So I multiplied that times 10 and got 8.66. And then multiplied that by 2 and got 17.32 meters. So this right here is how I would solve for how far it went. It wasn't in the question. But since we've got all the rest of the stuff we need to solve for that easy answer, I thought I'd just do it for practice. Okay?